Hi, this is Anna Doblas, and today we're gonna discuss the first video of Fourier optics, where we're gonna introduce the principle of Fourier optics and the relationship between the space and the Fourier domain, and the definition of linear optical systems and linear shift-invariant systems. So I just briefly say that we're gonna describe any optical signal as a combination of tilted plane wave. We're gonna describe linear optical systems and shift-invariant optical systems. I'm gonna introduce to you some steps to identify if an optical system is linear shift-invariant or not. Because if it's linear shift-invariant, then we can express the output as the convolution of the input and the input response. And I'm gonna give you a brief introduction about the image process using Fourier domain. So the principle of Fourier optics is that any optical signal can be decomposed as the superposition of harmonic functions which have frequency which are related with the frequencies u and v. So, and in other way, any signal can be decomposed as plane waves, tilted plane wave when we change the period and also the angle. And that means that in Fourier optics, our plane wave, and again, can be tilted plane wave, but plane wave are our eigen functions. So as I was kind of saying, the key is the plane wave, right? And a plane wave, if we remember module 2, it was this linear complex exponential, where now our value u and v, these u and v are our spatial frequencies. U and v are our spatial frequencies, but the spatial frequencies, as we are showing here, is gonna depend on the angle, on the tilt of the plane wave. So the spatial frequencies u and v related to the tilt of the plane wave. There is a mathematical derivation that I believe is nice and pretty, where you can have an interferogram, which is like the interference of two plane wave, and you know that the interference is going to have a tilted plane wave, and you can determine the angle of the two waves analyzing the Fourier domain, just because we know that they are related. So linear optical systems, why is super important having linear optical systems? And let's talk about a little bit the kernel. So we have our input plane. We have here our input and our output, and we don't know right now what is the transformation, but we know that the system is described by a S operator. So the operator of the system acting on your input provides your output, and the system is linear if the combination, a linear combination of two different outputs, is gonna be the same as the same combination with the respective outputs. And that means that the system operator does not change with the input. The same way, we're gonna define that the system is shift-invariant if the response of the system does not change if the input is shifted or not. So if that means that if you shift the input, it's exactly the same as having the original output shifted. There is this video on YouTube that provides additional information if you want to to know more about it, but I want you to approach this as a system, as any kind of system and any kind of signal. So that's what we're gonna know. So what is the key advantage? So how we know if a system is linear shift invariant, right? So we're gonna assume that we have here a delta. So on the input plane we have a delta, and then when the system acts on the unit impulse, that is our input response. So the input response is the system output to a unit impulse. And the system is linear shift invariant if the system output is the same regardless the location of the unit impulse. So that means that if you shift your unit impulse, you're gonna have the same shift in your input response. And only, and this is really important, only when the system is linear shift invariant, we can express the output as a two-dimensional convolution between the input and our input response. That's why it's super important when we have a system to determine if the system is linear shift invariant or not. Because if it's not, we cannot have this convolution. But if it is, it simplifies a lot because we treat this optical system as any system that we have previously learned about it. We use the same trick. So how are we gonna know if a system is linear shift invariant? So the first step that you need to do is you need to estimate the input response as the output of the system when your input is a center unit delta, it's a center delta function. Then your second step is you estimate your shifted input response as the output G when now your input is not anymore your center unit, it's just your displaced delta. And now your step number 3 is you're gonna compare the output from step 1 and 2. If we have the same output, but we have replaced x by x minus alpha and y by y minus beta in step 2, then the system is linear shift invariant. If not, if we don't have the same response with a simple shifting, then that means the system is space variant, and then the output is not gonna be your input with your input response. If I want you to see that when we do this procedure, this one, step 1 is how we estimate your input response that you're gonna use for the convolution. Right here, if the system is linear shift invariant. Alright, so this is the duality that is really important in Fourier optics, where you can analyze everything in the space domain. So you are in the space domain, you know that the output is the 2D convolution of your input when the input responds, or you can go to the reciprocal of your Fourier domain when you know that the output spectrum is the product of your input spectrum with a transfer function. So the transfer function, it tells you which frequencies of your input and how those frequencies are transferred from your input plane to your output plane. So it's completely another representation of the same problem. And I want you to kind of give you here an example. So let's assume that you have an object, right? And your object is composed by a lot of cosinusoidal patterns, right? And because every cosinusoidal, when we do to the Fourier domain, so when we do the Fourier transformation, right? If this is my object, this is gonna be my Fourier transform. I'm gonna have 2 deltas for each cosine. So at the end, I have I have like a line of a lot of unit deltas, and I'm multiplying here by my transfer function. So let's assume that my transfer function is this bow tie. And when I do this product, when I do this multiplication, this is gonna be the output spectrum. So you see that because we are completely centered on the bow tie, right? We only have a unit delta is going through the system, and then our image is completely wide or uniform, meaning that we have lost completely all the spatial frequencies of the cosinusoidal except one, which is kind of like doing a uniform. So this is kind of like the whole process of the imaging when we do it in Fourier domain. So we know that the output is the product of our input with our transfer function, and then we do the inverse Fourier transform to estimate our input distribution. So as you see, this is super close what we have been exposed in classes of signal and systems. Keep tuned to watch the rest of the videos about Fourier optics. Thank you.